Hello everyone, welcome to our next lecture in our Material and Energy Balance class. In the previous lecture, we just covered some very basics and a review of general chemistry. We introduced this idea of C, this extent of reaction, and today we're going to put it right into our material balance problems, and this is in section 4.7a to 4.7e, pages 140 to 150 in your textbook. So what we're going to do in this lecture is we're going to cover three different ways of doing our degree of freedom analysis and our material balance problems. Right now, what I'm going to do is to give you an overview of the three different ways of doing our degree of freedom analysis. After that, we'll jump right into an example and we'll highlight the three different ways of doing it, doing the DOF, and then do the actual problem itself. So the first method of doing our degree of freedom analysis with chemical reaction is the molecular species method. Think of this as the same method we have been doing before we even added chemical reactions. So the first step, which is going to be common for all methods, is we count the number of unknowns. So we draw our diagram, we circle the unknowns, and we figure out how many unknowns are there in each system or subsystem. What is new here is once we have a chemical reaction, for molecular species method, we need to add the number of reactions. So every chemical reaction is going to give us one additional unknown. So if we have 3 reactions going on in the reactor, we'll add 3 different unknowns to that. Once we have that, the rest are essentially the same for molecular species. We count the number of molecular species. This will give us the number of balances that we can write. And then we have all our other equations. We have our process specifications, we have physical laws, we have physical constraints, everything else that we have used before. This is the degree of freedom for the molecular species method. The only thing new is highlighted in red. Now we're adding more unknowns to this. Each reaction will give us one additional unknown. The second method, which is new here, is our atomic species method. In this case, instead of doing balances around every single molecule that we have, we're going to look at the atoms that are going in and out of this system. In terms of atoms, once we start to do the balance, and I'm going to say this again, atoms cannot be generated or consumed, which means doing our atomic balance is always going to be in equals to out when we have a steady state. Once we start to do an example, I will highlight this point again. In terms of the degree of freedom, we're going to start in the same place, number of unknowns. Now in this case, we don't care how many reactions there are. We're only looking at what goes in and what goes out in terms of the atoms. So we do not add the number of atoms, we do not add the number of reactions. The next thing we're going to count is the number of species, but we don't count molecular species, we count reactive atomic species. So we look at our chemical reaction equation, see what atoms are participating in this reaction, and those are the number of atomic species that we have. In many cases, some of our reactors might have an inert, so it could be nitrogen, it could be argon, some kind of gas that it does not participate in the reaction, it goes in and out. In this case, we do not look at the atoms, we look at it in terms of molecules. Again, this goes back to before chemical reactions, it's just in equals to out. So we need to count the number of non-reactive molecular species. We're just going to do a molecular balance down there. From there, we just have our other equations like we did before, process specifications, laws, physical constraints. So again, the ones that are new are the 2 that are highlighted in red. We're counting the reactive atomic species. We are subtracting the inert or non-reactive molecular species. The last method is the extent of reaction method. We talked about this extent of reaction, XC, in the previous lecture. This is going to be very similar to the molecular species. So we have the number of unknowns, we're going to add the number of reactions, that's what we did in molecular species. The only difference between the extent of reaction and a molecular species is, in terms of the molecular species that we count, we're going to split them up. We're going to split them into reactive and non-reactive. The reason why we do so is because if you go back to the previous lecture, there is a certain way in which we write our extent of reaction equations for reactive species. For the non-reactive species, it's just a simple in is equals to out. So this helps us to keep track of what the equations are we are going to write. So we're going to count the number of reactive molecular species, count the number of non-reactive molecular species. You can consider the summation of these two as equivalent to what we have up here in the degree of freedom for molecular species. So after that, we have the other equations, and that will give us our degree of freedom. All right, before we jump into our example and showing the degree of freedom analysis and solving each in each different method, the important thing to note here is that the result for degree of freedom must be the same regardless of which method you use to calculate a degree of freedom. The degree of freedom tells us whether or not we can solve the problem. If not, how many pieces of information do we need in addition to what we have? So regardless of the method you use, this should not change. And then this is important because we're going to see in some cases you end up with a different number, and you might need to go through the process of thinking about what's going on and what went wrong, or what have you not considered in a certain method that you have. The next important thing to note is you might be looking at the degree of freedom in a certain way. For example, you might look at the degree of freedom from a molecular species method, but when you actually start to solve the problem, you might prefer to solve it using the atomic method, and that is fine. The degree of freedom analysis, all it tells you is whether or not you can solve it or how many pieces of information that you need. All right, with that, let's jump into our example. This is example 4.6-1. It's taken from the textbook, page 134. If you read through the textbook, it presents it in one way only. What I'm going to do is I'm going to use this example and go through all three different methods, solving it in all three different ways to show you that you'll get the same answer. All right, so in this example, the primary means of synthesizing acrylonitrile is the oxidation of propylene. So we have the equation that's given there. We're given that the feed to this process contains 10 mole percent propylene, 12% ammonia, 78% air. And you'll see that what we need is oxygen that's in the air. So we're going to assume that 21% of the air is oxygen, 79% is nitrogen. We'll do that math in a bit. We are told that the fractional conversion of the limiting reactant is 30%. We are told to take 100 mole of feed as a basis. We want to find what reactant is limiting. Once we have that, we know which two are in excess. We want to find the percent excess of each of the other reactants and the molar amounts of all the products, given that we have this 30% conversion. All right, so before we start drawing the diagram and labeling it and solving for the molar amounts, the limiting reactant and the percent excess, we don't have to do any of that first. So let's go ahead and do that first. So before that, like I said, we're going to split up the air into our oxygen and our nitrogen. We know that oxygen is 21% of the air. So in terms of the mole fraction, it is 21% of the 78% that is in the feed. So the mole fraction of oxygen is 0.164. Do the same for our nitrogen. 79% of the 78% is nitrogen. So our mole fraction of nitrogen is 0.616. Now we have three different reactants, C3H6, NH3, and O2. We want to find which of these three is the limiting reactant. And the way you do it is think of it as one game playoff. So think about it as baseball. Those of you who are baseball fans, the wild card round. You have two teams pitted against each other. The winner moves on to the next round and plays the next round and decides who wins from there. So we'll do the same thing down here. To find the limiting reactant, I'm first going to pit C3H6 against NH3. So we're going to compare these two first. So the number of moles of C3H6 in the feed is 10% of 100. Number of moles of NH3 is 12% of 100. So we have 10 moles of C3H6 in the feed versus 12 moles of NH3 in the feed. How do we know which one is in excess, which one is limiting? We're going to compare with the stoichiometric coefficients. In this case, if you look at the chemical reaction, it is 1:1. So from stoichiometry, it is 1:1. You see that the actual ratio, 10/12, is less than 1:1. What this means is that we have too much of the component that's in the denominator, which means NH3 is in excess over C3H6 or C3H6 is limiting. There's less C3H6 than what is needed to fully consume all your NH3. Don't worry too much about, well, if it's less than the stoichiometric ratio, is it the bottom or the top that's limiting? Just walk yourself through verbally about what's going on. For example, in this case, we have 10 moles of C3H6. Based on stoichiometry, 10 moles of C3H6 requires 10 moles of NH3 to fully consume it. We have 12 moles of NH3, which means we have extra NH3. NH3 is in excess over C3H6. So just kind of walk yourself through the process that way. So we want the limiting reactant. NH3 in its excess, so the winner in this round is C3H6. That goes to move on to the next round. We're going to have it against O2. And here we have the number of moles of C3H6 versus number of moles of O2, and it's 10 over 16.4. We are going to look at the stoichiometric coefficient. In this case, the stoichiometric coefficient for O2 is 1.5. And once again, you see that the ratio is less than what is the stoichiometric ratio. So what this means, again, is that we have too much of the component in the denominator. Walk through this again yourself. Stoichiometrically, 10 moles of C3H6 will require 15 moles of O2 to fully react with it. We have 16.4 moles of O2, so we have excess O2. So O2 is in excess over C3H6, which means from here the winner is our C3H6. That's the limiting reactant. Once we have C3H6 as the limiting reactant, we can find the percent excess of our other two components, our ammonia and our oxygen. Here, I've just repeated the equation for percent access. This came from our previous lecture. It is how much we fed in minus how much that's actually needed to react all of it, divided how much actually needed. All right, so to find the percent access of NH3 and O2, we know how much is fed in. That's already given in the question, or it's one of our variables. The main thing is how do we find what is stoichiometrically needed. From stoichiometry, we saw that the limiting reactant C3H6, that's 10 moles of it, we require 10 moles of NH3 for complete conversion, which means stoichiometrically we only need 10 moles of NH3. So the percent access from here, by putting it into the equation, we have 12 moles, we only need 10 moles, so 20% of, we have 20% access of NH3. We do the same thing with O2. So from stoichiometry, 10 moles of C3H6 requires 15 moles of O2 for complete conversion. So the stoichiometric amount of O2 that's needed is 15. We have 16.4, so the percent access of O2 is 9.3. All right, so we have solved the first two parts of this. Now we can go ahead and go through the problem, draw the process flow diagram, label the diagram, circle our unknowns, do our degree of freedom analysis, and then start solving the problem. So let's go ahead and do that. So now what we're going to do is try to do our process flow diagram. We're going to draw the process flow diagram, and then we're going to label it, circle our unknowns, and then go ahead and do our degree of freedom analysis. So as usual, what I like to do is to first draw the skeleton of this process. In this case, we're still in a single unit system, so it's rather straightforward. All we have is a single reactor. So we have a reactor right here, and we have one stream in and one stream out. We have our feed stream that's coming in, and we have a product stream that I'm going to label as stream 1. And what I like to do as well is to just transfer our chemical reaction equation on the top, so to remind myself that what is going on in this reactor. So in this reactor we have C3H6 reacting with ammonia and oxygen to give our acrylonitrile. And we also have water as our byproduct. All right, so that's the equation, or that's the chemical reaction that's going on within the reactor. Now that we have the skeleton of the system, we're going to go back to the problem and read through and transfer any of the information that we have onto this diagram down here. We are told that the feed to the process contains 10 mole percent propylene, 12% ammonia, and 78% air. And we have already done the math. Within the 78%, we know that 21% is oxygen. And so the mole fraction of oxygen is 0.164. We did that for nitrogen, which is 79% as well. So let's go ahead and label that. So we're given the feed composition down here. So we know the mole fraction of C3H6, and this is 0.1. We're given the mole fraction of ammonia, 0.12. We have divided up the air into oxygen, which is 0.164, and our nitrogen as 0.616. Okay, so we have the compositions that's given to us. A fractional conversion of 30% of the limiting reactant is achieved. That is a process spec that we can use eventually, but now we don't have, we won't have to do anything in terms of labeling the diagram here. We are told to take 100 mole of feed as a basis. So we are given a basis down here, which means this is 100 moles, and this is our basis. All right. Given that piece of information, that is all that we are given. Everything else is unknown. So now we need to figure out on this diagram what is coming out in stream 1 out here. What is the product? First of all, let's look at what's going in and decide, based on what's going in, what else will be coming out from our inputs. Nitrogen is definitely going to come out because it's an inert, so it's not participating in the reaction. In this case, we said that there is a 30% conversion of the limiting reactant, which is our C3H6. And when you have a fractional conversion of your limiting reactant, so even if your limiting reactant is not fully consumed, that means all your other components that are in excess is not going to be consumed as well. So because of that, we know that everything that's going in is actually also going to come out. So let's label that first. We know that we have the number of moles of C3H6 coming out. That is the amount that's unreacted. Number of moles of ammonia that's unreacted. Number of moles of oxygen, and nitrogen is our inert that's going to come out as well. So now we have figured out what went in that's still going to come out. At the same time, we also have our products, our acrylonitrile and our water. So that's going to come out as well. So we have our acrylonitrile and our water. And that's how we figure out what is going to come out of our reactor. Based on what we put in and based on the reaction, we know these are the things that are going to come out. So the next step is to circle our unknowns to know, so that we know where they exactly are. They're all on this side. We have 6 unknowns. Now we can go ahead and continue with this problem by doing the degree of freedom analysis. We're going to present all 3 methods to see how they are different, and then we're going to do the problem using all 3 methods. Alright, so here's our completed process flow diagram and everything labeled. All our unknowns are circled on the right. You can see all our unknowns in this case are just on the right hand side, what's coming out of the reactor. So now let's go through the degree of freedom analysis first and verify that we can get the same degree of freedom for each. In this case, it's going to be 0 because we need to solve this problem. For the molecular species degree of freedom method, first thing is count the number of unknowns. This is common for all methods, and we have the 6 unknowns that's circled on the right hand side over there. The next thing we do for molecular species is add the number of reactions. In this case, we only have 1 reaction, so we're going to add 1 reaction. Next thing we do is to count the number of species. That will give us the number of balances we can write. And we have the 6 species. So the 6 species are essentially the 6 things that are coming out from the reactor. So we have the 6 different species here. After that, we have one more thing. We have the process specification, which is the fractional conversion of the limiting reactant, C3H6, is 30%. Going back to the definition of fractional conversion, it is the most that has been reacted over most fed. The most reacted is what you fed in minus what came out. So C3H6 in the feed minus C3H6 in stream 1. And this equals to 30%. So you can start from here and then rearrange this equation to solve for whatever unknown you need. Or the easier way is to think about it differently and kind of skip a step ahead to rearrange this right away in a form that's a lot easier to manipulate and solve. And that's this way. The fractional conversion is how much has been reacted. So if 30% has been reacted, that means 70%, or 1 minus 0.3, comes out. So one way to think about this is the amount that's coming out is 1 minus the fractional conversion of what went in. So by writing it this way, this equation is essentially a manipulation of the earlier equation you see down there, but it's in a form that's a lot easier to understand, it's a lot easier to manipulate. So from now on, I'll actually write my fractional conversion in that way. If you can't understand or if you're a little confused about what's going on there, just go back to the definition of fractional conversion. All right, 6 plus 1 minus 6 minus 1, we have a degree of freedom of 0. We're going to solve this once we finish all the degree of freedom analysis. All right, let's move on to atomic species. So this is one of the new ones. We have the same 6 unknowns. For atomic species, we do not add any reaction. We look at the number of reactive atomic species. So what are the reactive atomic species? If you look at the chemical reaction equation down here, we have carbon, hydrogen, nitrogen, and oxygen. These 4 atoms are participating in this chemical reaction. So we have 4 reactive atomic species. We also have an inert, which is our nitrogen gas. Our nitrogen gas goes in and it comes right out. It is not participating in this reaction, so we can do a balance there. So we need to subtract 1 non-reactive molecular species. After that, we have our process specification that we talked about, the fractional conversion. 6 minus 4 minus 1 minus 1, that gives us our 0. Lastly, we have our extent of reaction. Again, I mentioned this earlier. This is going to be very similar to our molecular species method of DOF. 6 unknowns, add the number of reactions is 1. Now, instead of just counting all the molecular species, we're going to split it up into reactive and non-reactive. Number of reactive species, how you figure that out? Look at the chemical reaction equation. See how many molecules are there in the reaction. In this case, we have 5 different molecules. C3H6, NH3, and O2 are our reactants. C3H3N and water are our products. So we have 5 reactive molecular species. We're going to write extent of reaction equations for those. Then we have a non-reactive molecular species, just like in the case of the atomic, which is our nitrogen. This is just our simple in equals to out. Then we have our process specification, 6 plus 1 minus 5 minus 1 minus 1. That gives us our 0. So it is consistent across all different methods. But again, I like to use this degree of freedom analysis to guide me in terms of what are the equations that I have. So now let's go ahead and solve this problem using all 3 different methods. And let's start with the molecular species method. All right, I've repeated the molecular species DOF on the right-hand side here because that will give us an idea about what are the equations we can use to solve these 7 unknowns. So let's start with the process specification. We already know what this is. The number of moles of C3H6 coming out is 1 minus the fractional conversion multiplied by what went in. We already have what went in, so we know that we have 7 moles of C3H6 that's coming out. That allows us to solve for one of them. So we're done with the process specification right here. And in terms of the inert, we can do the inert by just doing an in equals to out. I'm going to start with the general balance again. So going back to when we first started on these, general material balance, accumulation is in minus out plus generation minus consumption. We know that accumulation is 0. We're assuming a steady state process. For nitrogen, it is not participating in any of the chemical reactions. So it's non-reactive, generation and consumption are 0. That is how we end up with in equals to out, which is what we have done earlier before chemical reactions. We know what went in, we can figure out what went out, and so we have 61.6 moles of our nitrogen that's coming out. All right, so far what we have done, nothing new. We have done all of these balances before. So now let's look at something that's new, which is one of our reactants, our C3H6. Starting with our general balance, accumulation in minus out, generation plus minus consumption. We don't have accumulation, it's steady state. We have C3H6 coming in. We have C3H6 coming out. It is not being generated, but it is being consumed in this reactor. So in this case, our balance has one more term to it. 0 is in minus out minus consumption. We know what went in, that's in the feed. We know what came out, which is what we're trying to find. Now we have this consumption term down here. And if you remember our degree of freedom, we added this 1 over here, which gives us one additional unknown, and here is what the reaction unknown is. In this case, it is cast in terms of C3H6, is the consumption of C3H6. So I'm using big C as consumption, and the subscript refers to the species I'm talking about. So in this case, we already know what the C3H6 coming in is. We know what came out, so we can calculate the consumption of C3H6, which is 3 moles down here. All right, so that's our C3H6 balance. Let's move on to the next reactant, which is our NH3. It's the same thing. We have no accumulation and there's no generation, but we are consuming NH3 in our process. Let's put in our variables here. We know 12 moles went in. We are trying to calculate how much is coming out. But in this case now, we have this consumption of NH3. So how are we going to figure that out? We only have one reaction unknown. By stoichiometry, we can relate this consumption of NH3 with the consumption of C3H6, which we already found up in the previous step. So from stoichiometry, looking at the chemical reaction equation, consumption of C3H6 is in a 1-to-1 ratio with the consumption of NH3, so it's just the same. It's equals to 2/3 the consumption of O2, and it is also equals to the generation of C3H3N, it's a 1-to-1, and then 1/3 the generation of H2O. Some of you at this point might be asking yourselves, why did I flip the stoichiometric coefficients? In the chemical reaction equation, it's 3/2 for oxygen. Why is it 2/3 over here? The way I like to process through this really slowly is just writing it in terms of a ratio. So if we write it in terms of a ratio, the consumption of C3H6 to the consumption of O2, this is where we look at the stoichiometry from the equation, is 1/3/2, or 2/3. So if I rearrange this, you'll see why it actually is 2/3 instead of 3/2. So don't worry too much about is it 2/3, is it 3/2, just go ahead and write it in terms of the ratios and go through this process step by step. So with this, we know that this is essentially equals to the consumption of C3H6, which we already have as 3 moles above. We can solve for the number of moles of NH3 that's coming out, which is 9 moles. All right, so we're going to keep going for oxygen and our products. For oxygen, it's the same thing. I'm going to skip through this really quickly. Same balance equation. It reduces to in minus out minus consumption. The consumption of O2, we relate it to the reaction unknown we already found. So it's 3/2 times the consumption of C3H6. With that, put in all the numbers, and we end up with the number of moles of O2. Let's move on to the products. So the products is going to look a little different. So for C3H3N, we don't have any product coming in. We don't have any product that's being consumed, or we do have product getting generated. So what we have in this case for our balance is 0 equals to minus out plus generation. We know the out term, that's what we're trying to find. What is being generated, we can relate that to the reaction unknown that we found. And so we know the generation of, or the number of moles of C3H3N coming out is just 3 moles. All right, finishing up with H2O. Now, same thing, 0 equals to minus out plus generation, starting from the material balance, overall general balance. And we have the variable for number of moles of water coming out, and the generation term, we'll relate that to our reaction unknown and solve for the number of moles of water. All right. Some of you might be looking at this and realize that this feels a lot intuitively like just using stoichiometry to solve a reaction problem like you have done in general chemistry, and that is true. But what I'm trying to illustrate here is doing it step by step using a material balance, starting with this general balance. And this will come into play, and this will be important once we start to increase the complexity of our problems by adding multiple reactions and eventually putting it into multiple units, which is where we're going with this class. So bear with me as I kind of walk through this slowly, step by step over here. One thing I want to point out right here now is, if you recall in one of my earlier lectures, before we start to talk about reactions, I always mentioned that you should think about doing an overall balance. Even though we are counting the number of species to give us an idea of how many balances we can write, I always say remember to think about an overall balance, because an overall balance in general, it's simpler, it is less complex, it has less unknowns in it. So in general, it'll be easier to solve. I'm going to go back on all of that because when we talk about chemical reactions, you do not want to do an overall balance. If you think about overall balance in this case, you might be tempted to say, well, I have 100 moles coming in. I have all these things that are coming out in stream 1, so they must be equal. But they are not. And why are they not equal? Because if we think about the overall balance, start from the general balance, assuming steady state accumulation is 0, but none of the other terms are 0. It's not just in equals to out anymore. We have all the non-zero generation and consumption of every single species. So think about adding the G's and the C's for every single species into this equation. It makes it really complex. It is useless, so do not write an overall balance when we start to do chemical reactions. All right, so that's the molecular species method. It's the same method we have been doing before this, now just adding reactions to it, so our generation and consumption may or may not be 0 in this case. Now let's look at the atomic species method. I'm not going to repeat the specification and the inert because it's the exact same thing. We're going to solve the specification in the exact same manner as we did earlier. The inert, same thing, 0 equals to in minus out. So we have the nitrogen balance. So looking at our degree of freedom, we have completed our process specification. We have completed our non-reactive molecular species. So the remaining 4 tools that we have to solve for our remaining 4 unknowns are our 4 reactive atomic species. So now let's start with the carbon balance first. Going back to our general material balance, in this case, we are always going to assume steady state for the purpose of this class. For atomic species balances, generation and consumption are always going to be 0 because atoms cannot be generated or consumed. Now, carbon might change partners, so it might appear in C3H6 in the feed, and it might go into C3H3N in the product, but it doesn't matter. All we are counting is the fact that if carbon goes in, it must come out somewhere, and there must be an equal amount of them. So in terms of atomic balances, it's always going to be 0 equals to in minus out. Where is carbon coming in? In the feed, carbon is coming in C3H6. That's the only species that has carbon in it. So the number of moles of C3H6 is mole fraction multiplied by the number of moles. But for every mole of C3H6 in this feed, we have 3 moles of carbon. We are counting carbon. So based on the chemical formula of C3H6, we know that every mole of C3H6 gives me 3 moles of carbon. That's why we need the 3 in front of that. So let's look at the product. In terms of product, we have C3H6 coming out that has carbon, and we have our product C3H3N that's coming out that has carbon. So we have 2 species down there. Again, look at the chemical formulas. There are 3 moles of carbon per mole of these molecular species. That's why we have the 3 in front of each one of these down here. And that will give us our carbon balance. One of the most common mistakes that I've seen is rather than looking at the chemical formulas for what goes in front of these over here, students have a tendency to make a mistake of putting the stoichiometric coefficients instead. So for example, 1 down here, and they'll put a 1 in front of that. when we talk about atomic species balances, there's a reason why we don't add the number of equations, because we don't care what reactions are going on. So don't look at the equations, look at what's coming in and look at what's coming out. So from here, putting in the numbers, you realize we only have one unknown, which is the number of moles of our product. We solve it, we end up with the same answer as we got before, which is 3 moles. All right, now let's go on to our nitrogen balance. Same thing, 0 equals to in minus out. And now nitrogen is coming in ammonia. It's coming out as ammonia and coming out in our product C3H3N. Now, the important thing to note here is you do not want to include our diatomic nitrogen. Remember, we have already accounted for that. We consider it a non-reactive molecular species. So let's look at our degree of freedom here. See that we have split them up down here. There is a nitrogen that is participating in the reaction, and that comes from ammonia and C3H3N. There is nitrogen that is non-reactive, that's just diatomic nitrogen that goes in and out. We have already accounted for that, we have already solved for that. So do not include that in our nitrogen balance here. Then we have our 3 terms down there. In this case, the chemical formulas, there's only 1 mole of nitrogen in each species. From here, we only have 1 unknown left, is the number of nitrogen ammonia coming out. You can solve that for 9 moles. All right, we have 2 more atomic species to go, our hydrogen and our oxygen. Hydrogen, again, is always going to be 0 equals to in minus out. Now take some time, pause this video, and write out all the terms that we have. Once you're done with that, start this video again and double check your answer. Okay, hopefully you have a chance to try that. Let's double check your answer over here. You'll realize that we have quite a few terms in the hydrogen balance. Hydrogen is coming in C3H6, NH3, and it's coming out C3H6, NH3, C3H3N, and H2O. So you have 6 different terms. And for every mole of C3H6, you have 6 moles of hydrogen. Every mole of NH3, you have 3 moles of hydrogen. So on and so forth, that gives you the coefficients in front of each term. So double check those with the work that you have tried. Once you have that, it looks really long, but actually there's only 1 unknown that's left. Everything we have solved for, the number of moles of water is 9 moles. All right, to finish this up really quickly, here's our oxygen balance. For every diatomic oxygen, you have 2 moles of oxygen. So we have that. Oxygen also appears in water, so we have that term coming out. Putting everything in, we have 1 unknown left, which is the number of moles of oxygen that's coming out. Double check these answers. They're going to be the exact same as what we had in the previous example, using the molecular species method. All right, now let's move on to the very last method, the extent of reaction method. From before, I'm not going to repeat this again, the specification gives us the number of moles of C3H6 coming out. Our inert balance gives us the nitrogen that's coming out. This is going to be the same for all methods. So looking at our degree of freedom, we have used our process specification, we have done our non-reactive molecular species. We are down to our 5 reactive molecular species balances. And what are these balances? These are our extent of reaction equations that we covered in the previous lecture. So let's start by writing the first one as a recap. How do we write our extent of reaction equations? What comes out is equal to what went in plus or minus the extent of reaction depending whether it's a product or a reactant. And then you have to include your stoichiometric coefficients in front of that Xc. In this case, the number of moles of C3H6 coming out is equals to what went in, and minus because there's a reactant, and the coefficient down here is just 1. So the coefficient in front of Xc is just 1. In this case, you can see where our reaction unknown is. Remember, in a degree of freedom, we added this plus 1, which means we're solving for 1 additional unknown. The reaction unknown turns out to be our Xc. So we have our other 4 equations. We have our 5 reactive molecular species. We can write out our other extent of reaction equations. So go through them and make sure you can understand what's going on. For example, in the oxygen, it is a reactant, so it is being consumed, so it's a minus. And then we have a stoichiometric coefficient of 1.5, so we have that in front of the Xc. For hydrogen, we have a stoichiometric coefficient of 3, and it is a product, so it's a plus 3 over here. And we didn't put any water into the reactor, so that's 0. All we need to do is to solve for these 5 equations and solve for our unknowns. Looking at these equations, you realize that from equation 1, we can solve for our reaction unknown right away, Xc as 3 moles. Once we have that xc, we are pretty much home free. If you look at every single equation, if we know xc, we can just put in all of them and we can find the number of moles coming out. So you can do that, double check that, and you'll realize that we have the same answer as we did in the previous two methods. If you think about this, and as you're doing this, you might think this feels a little similar to the molecular species. It feels a little similar to what you would think about as you are doing it from a general chemistry standpoint, and that is true. All we are doing is presenting in a way using a variable called extent of reaction to present this question. It is essentially the same method you have been doing through general chemistry. All right, before I end here, I want to talk about one really quick note, which is this independent balance in atomic species. What you're going to find as we do more and more of these problems is the most often where you'll find your degree of freedom that is not consistent with the other methods is the atomic species degree of freedom, because whether they are independent is less obvious. But one of the obvious ways I'm going to present right here. So let's do a quick recap. Recall that for molecular species balances, we looked at this from the perspective of a splitting point. We saw that if any two molecular species are in the same ratio in all streams around a system. So for example, if I have an ethanol water mixture in the ratio of 2 to 1, I take this feed, I split it into two, A and B. These two, A and B, are also going to have ethanol and water in the same ratio 2 to 1, because all I'm doing is taking this, making it into two. Right? So all three of them, all three streams, the feed and A and B, are in the same ratio of 2 to 1. We saw that when that happens, we don't have the number of balances to write equals number of species. We only have one independent balance. We just have the overall balance. So in that case, the molecular species balances are not independent. Likewise, for atomic species balances, if any two atomic species are in the same ratio in all the species around a system, those species are not going to be independent. So as a quick trivial example, here we have an evaporation of carbon tetrachloride. So we have liquid carbon tetrachloride coming in stream 1. Some of it is evaporated into stream 2. Some of it is left as a liquid in stream 3. In general, in this case, there's no reaction, so generally we will not even do an atomic method, we will just do a molecular method. I'm just using this as an example to highlight what I mean by a non-independent balance. Let's do a carbon balance. Carbon balance would be N1 minus N2 minus N3, because in N1, the number of moles of CCl4, per mole of CCl4, we have 1 mole of carbon. Same for N2 and N3. Let's do a chlorine balance. Per mole of CCl4, we have 4 moles of chlorine, so we have a 4 in front of all of them. But very quickly you realize that I can just divide the 4 away, and you end up with the same equation. And this is what I mean by the fact that when you have two atomic species that are in the same ratio in all the streams, in this case 1, 2, and 3, in all the species, they are not independent, you end up with the same equation. So in this case, number of moles of carbon over the number of moles of chlorine in 1, 2, and 3 are essentially the same, and because of that, the carbon and chlorine balances are not independent. All right, so that's all we have for this lecture. Hopefully you find this helpful. Go back and review the 3 different methods of solving this. In the next lecture, we're going to add a layer of complexity to it by looking at multiple reactions, not just one. And from there, we're going to keep adding more and more layers of complexity to our question, finally building up to multiple processes, multiple units to this. So work hard, be smart. I'll see you in the next lecture.